Hello and welcome back to ENAE 788M, Hands-on Autonomous Aerial Robotics. In this lecture, let's talk about what are features in computer vision. So visual features are something that we can say, okay, these are the features or these are the key points in the image or key edges in the image or something like that could describe these images, right? This can be edges, this can be corners, this can be blobs, this can be descriptor. We'll talk about one by one after we go through these. Okay, and let's move on. So if you see there that this is a corner, right? This corner would be very specific to, let's say this is an India gate, right? You won't find these things in, for example, Statue of Liberty. So if I have another image from another view of the same India gate, I could match these features and maybe create something out of it. Let's see what these visual features can be important. So you see these green crosses, these are corners which are detected in the images. So why are features important? So let's say you take 4 images like of a scene. Let's say this is the Delicate Arches National Park. So you take 4 different images, and you don't have a very wide field of view in the camera, right? So what you're gonna do is you're gonna use these 4 images and stitch these images by matching the common feature between each two. So let's say you can see in this image and this image you have common features, in this image and this image you have common features. So you keep expanding your horizon, and basically you're going to match features between 1 and 2, you're going to match features between 2 and 3, you're going to match features between 3 and 4, and so on, and you'll get something like this. So this is why your visual features are very important. Okay, so another example is if you have a bunch of images of the same thing. So you have this building and you have like 20 of these images, right? You can also, by just doing or detecting feature and matching them, you can also recreate the 3D structure out of it. So just using those 20 images from a random position and orientation of unknown random position and orientation, let's say, you can create such a structure. All these yellow dots you're seeing here are the pose of the camera where the images would have been taken from. So you can reconstruct the entire 3D model of the object and the points where you took the images. So this problem is fundamentally known as structure for motion. So you're recreating the structure from different poses. So let's talk about edges. So we have discussed in the previous lectures that edges can be computed using convolution. One of them we read about was Sobel, Pruitt, and Robert. And we also talked about the Canny, which is more adaptive in nature. These three had fixed matrices which were convolving with the images, or kernels which were convolving with the images, and Canny had an algorithm which was adaptively trying to find what are the edges in the images, right? So in Sobel we had, like, if you want to find the edge in the x direction, and if you want to find in y direction, we can just convolve given these two kernels, right? So Canny was a multi-stage algorithm. It uses calculation of variation. It's a technique which basically finds the function which optimizes a given functional. So Canny as detector describes a sum of 4 exponential terms as the optimal function, and finally basically approximates a long equation by just the first derivative of the Gaussian. So basically just think Canny as an adaptive Sobel, if you will. So let's talk about why are the Gaussian filters very important for edge detection. So as both the edge and noise will be identified as high frequency signal, simple Gaussian filter will add a smooth effect on both of them. However, in order to reach high accuracy of detection of the real edge, it is expected that more smooth effects should be added to noise and less smooth effects should be added to the edges, right? So there's a thing called in I think early 2000, Bing Wang and Xiaosheng Fan from Changsha University of Science and Technology, they developed an adaptive filter where the filter will eventually evaluate discontinuity between grayscale values of each pixel. So the higher the continuity is, the lower the weight value is set for the smooth filters at that point. So contrary, the lower discontinuity between the gray values, the higher the weight value is set to the filter. So whenever you are using Gaussian, just be aware that if the signal has not very strong edges, then your Gaussian will also basically filter noise as well as your signal or the main edges. So just be careful what Gaussian filter you're applying to your image, right? It shouldn't be like the sigma shouldn't be too high, for example. So you can use adaptive Gaussian filter like Bing, Wang, and Fan filters. Okay, so what is a corner? So we talked about edges, right? So let's say this is an image, right? And this is one edge. This is the other edge, right? So this point, which is the intersection of two edges, is defined as a corner of the image. So a corner can be basically defined as the intersection of two images. A corner can be also be defined as a point for which there are two dominant and different edge directions. So you see one edge direction here and you see one edge direction here, right? So corner or interest point or corner features, they are used interchangeably in literature. So these are several detectors which are also referred to as interest point operators sometimes. So a good corner detector is what? A good corner detector algorithm will detect the same corner in multiple images. Let's say we were discussing about the image of the India Gate, right? So you take an image from the first view that you saw, and I moved like 15 meters forward and rotated a little bit and take another snapshot, right? I should get the same corner. I should be able to match that corner from image 1 to image 2. So that's the property of a good corner detector, right? Even under the condition of different lighting and translation, rotation, and other transformations. So a simple approach to corner detection in images is using correlation, but this gets very computationally expensive and it's suboptimal, right? So an alternative approach used frequently is based on a method proposed by Harris and Stephens. Let's talk about that. So it's called Harris corner detector. So this uses the weighted sum of square difference or SSD between two patches. So you define patches like this. This is one patch and you have another patch on the another image. So the corner score is calculated for each pixel, and if the score is above a certain value, we call it a corner. If the score is calculated using these scores are calculated using two eigenvalues. These two eigenvalues are fed to a function which basically gives back a corner score. So depending on your threshold, it is selected or rejected as a corner. So this function is a nonlinear function. So it is also, to make it a little faster, it is also approximated by Taylor approximation. So there's another corner detector, very famous, called Shi Tomasi corner detector, and basically it's entirely based on your Harris corner detector. However, there's one slight variation in the selection criteria. So the selection criteria of Shi Tomasi corner detector makes it better than the Harris. So it works quite well where even the Harris corner detector fails. So unlike Harris corner detector, Shi Tomasi suggested that directly the eigenvalues should be used to check if the pixel was a corner or not, rather than feeding into a function for the corner score. So in Shi Tomasi paper, it is experimentally demonstrated that the score criteria was much better. Let's talk about blob detection. So a blob is a region of an image in which some properties are constant or approximately constant. So all the points in a blob, so you see these red circles, right? These are the blobs in the image. So all the points in the blob can be considered in some sense to be similar to each other. So one of the common way to detect blobs is convolution again. So one of the main reasons why blob detection picked up pace in research was to provide complementary information about regions which edge or corner detectors were failing to do so. So one of the most commonly used blob detectors is based on computing the Laplacian of Gaussian, commonly known as LOG, and can be well approximated by difference of Gaussian or DOG to decrease the number of computations. So feature detectors, so feature descriptors. So feature descriptors, are commonly known as visual descriptors or image descriptors, are the descriptions of visual features in an image. So these describe the fundamental characteristics like shape, color, texture. These are very commonly used in face recognition. So let's talk about image gradient, right? In this image, let's say this is the entire image I'm having, right? And I try to compute the difference or the image gradient at each pixel, something like this, right? Now what I do is, let's say my image was some x cross y, right? I divide my image into, let's say, 4 subsection, right? And now I compute the image gradient here. So we can see that this is the dominant gradient direction, this is the dominant gradient direction. So these gradients that I see here, like coming from here to here, represents one image descriptor. So this is one image descriptor for me. So what we commonly do is, like, we'll talk about the most basic image descriptor, for example. So the way you described is, let's say you have the corner or feature detection done already, right? So at each corner, let's say we take a patch. So let's say this was an image, right? And this is a corner. Let's say this image is about 800 by 600 or something like that, right? So I have these corners, right? A lot of corners in the image. Now what I do is, around each corner I make a patch of, let's say, 40 cross 40, and this is at the center, right? 40 cross 40 is not necessary. This can be 80 cross 80, 60 cross 60, depending on the image, right? So once you have this, what you're going to do is you subsample your blurred output. So let's say you had 40 cross 40, I subsample this image to something which is 8 cross 8. So I applied a Gaussian blur and then subsample it, right? So why I'm doing this is to remove noise by applying the Gaussian blur. So now I have an 8 cross 8 vector, and what I'm gonna do is this 8 cross 8 matrix, and I'm gonna just reshape this matrix as a 64 cross 1 vector, for example. So from 8 cross 8, I'm going to just reshape it to 64 cross 1. Now what I'm going to do is I'm going to standardize this vector to have the zero mean and variance 1. So this can be done by subtracting all the values by mean and then dividing by the standard deviation. So standardization, this is called standardization, and it is used to remove the bias and some illumination effect. So this 64 cross 1 vector which I have after the standardization is my feature descriptor. So you can use a lot of these feature descriptors between two different frames to match the features. Let's talk about the most commonly used feature descriptor today. It's called SIFT, or Scale Invariant Feature Transform. It's one of the most famous feature descriptor, and it was published and patented by David Lowe in 1999. And the fun part is the patent expired about 6 months ago in about March 2019, and every company was happy about this, that they can use this robust method of feature descriptor. So it is very commonly used today for robust matching, especially in robotics, right? And object recognition, mapping, gesture recognition, 3D modeling, and video tracking, stuff like that. So the idea of SIFT is you take an image, you blur that image and subsample it to half the resolution. You do it again, you do it again, you do it again. You keep doing it at multiple levels. So this is called a pyramid structural way to find feature, and it is very commonly used in computer vision. So you see, you take an image, you keep blurring, you subsample, you keep blurring, you keep blurring, you keep blurring, right? So this is a very common idea or generalized idea that people use in computer vision today. So what SIFT does it transforms an image into a large collection of feature vector, each being invariant to image translation, scaling, and rotation. So it is also partially invariant to illumination change and robust to local geometric distortion. So to detect these features, it uses the same difference of Gaussian DOG that we discussed and apply it to a series of smooth and resampled images. So after resampling, the low contrast candidate points, or basically feature points and edges, are discarded, and the dominant orientation are assigned to localized key points. So these the SIFT is robust to local affine distortion. So there's a thing called affine transformation. We'll talk about in the next class. Okay, for now, just make sure you know that SIFT is robust to local affine distortion. Okay. So this is an image, right? You see there is this car and the same car is here, right? And you see there's a most likely 90-degree rotation between these two. So if I run my standard Harris corner or the older corner detectors, you'll get something like this, right? So you see these features are incorrect for sure. You don't want these boxes to match my car because these are not the case, right? So what I want to do is using SIFT, let's see what happens. So you see, even if the car was rotated, because my SIFT is rotation invariant, I will get most of the features that I'll get will be corrected. Okay, so let's talk about the other common features used today in computer vision. So one of the common one is SURF, which basically approximates the difference of Gaussian with box filters. Box filter we discussed in the previous class that you basically have 1 1 1 1 1 1 3 cross 3 matrix into 1 by 9. That's basically everything. So box blurs are frequently used to approximate Gaussian blur. That's a very common thing. It's not as efficient probably or good as Gaussian blur, but for most of the cases it can be a very good approximation. So instead of Gaussian averaging, the image squares are used for approximation, since the convolution with square is much faster if the integral image is used. So this can be done in parallel for different scales. So SURF uses a blob detector, which is based on Hessian matrices to find the points of interest. So I'm not going into details about how these algorithms actually work, because each of these will at least take a class or two. So if you want to read it, feel free and go read about these things. So the next one is called fast features, which is features from accelerated segment test. So it is a computationally efficient corner detector, which is commonly used in robotics for real-time applications. So as the name suggests, it is basically fast and very computationally efficient. So especially when you are working with embedded devices which have limited computation, you want to use fast over any other algorithm. So it is much faster than SIFT, although not as robust. So it is also based on difference of Gaussian. It uses a concept from decision trees to make the detection faster. And fast does not compute any orientation, and again it is also rotation invariant. So there's another thing called orb. So it's a fusion of the fast key point detector that we discussed right now and another key detector which is called brief, BRIEF. It's a very also one of the newly famous corner detectors. So it basically combines these two. So initially to determine the key point, it uses fast and uses Harris corner detector for the first top endpoints, something like that. So there's a very famous SLAM algorithm called ORB SLAM, basically, which does a loop closure. So let's say you have a robot that starts from here. You are basically doing a square, something like this, and you know that this position and this position are the same, but there is a considerable amount of drift in your algorithm, right? So what ORB SLAM does is in the last step, obviously it's using all features, but in the last it has an optimization part which basically says that okay, these two parts are same, and this is a thing called loop closure. So it basically optimizes over the entire path, and it does something like this. So from this is after loop closure. This is what you get. So this is just the fundamental basics of how ORB SLAM works. Okay, so the reason why we are learning about features is feature matching, right? If I want to do panorama stitching or structure for motion that we discussed right now, you want to match correct features, right? But when you match features even using SIFT or something like good algorithms, you won't get correct features. You will definitely can get bad matching. So for example, this feature is matched with 5 different features, which shouldn't be the case for us, right? So these are the feature matching raw, if you want to call it, just matching the feature descriptors from one image to the other. So after that, you have to use something called a ransack that we have learned before. So if you do ransack, you are basically removing all the outliers, and the feature matches that you are left with are the good feature matches. Okay, so there's another thing called feature tracking. So let's see how this works. So for example, these are different cars, right? And if you see that each car has an ID or a number assigned to it, and that number is unique, right? That number is keeping that number constant, right? So if you see the car 11 from the beginning to the end, that was able to track this. So you can use feature matching for tracking among 2 frames. So let's say if you have a video sequence, you can use the first frame and the second frame and match these 2 features, right? So you can use feature matching that we have learned as feature tracking. The problem with that is it's slow. So people use something like KLT or Kanade-Lucas-Tomasi tracking algorithm. Why we do that is in your feature matching, you don't have any assumption that, okay, my 2 frames in a video are consecutive. You don't have any assumption, right? So it makes things very slow. So in KLT, feature tracker or any other feature tracking algorithm, you have an assumption that you have a continuous stream of images, or you have a video sequence. So in my first frame, let's say this car is here, right? In the next frame, my car won't be here, because it's a continuous stream, and I'm assuming that I have a relatively very good frame rate. So the car will move max from here to here, right? This is my assumption. Doing that, I can write a feature tracker, something like KLT, right? So that is the main difference between using feature matching as a tracker or actually using a feature tracking algorithm. So if you see that this point is being tracked over 5 different points, right? You're going from here to here, and you have this feature tracker over different continuous frames, right? So this is what Lucas-Tomasi, Kanade-Lucas-Tomasi feature tracker does. So this is the output of, let's say, 2 frames or 3 frames or n frames, if you want to call it. So the point you see, let's say this point to this point. This is from the frame 1. This is from the frame 2. So this green line is saying that, okay, this particular features move from this point to this point across the first frame and the second frame. So that's basically what your KLT feature tracking gives an output. So if you want to read about KLT feature tracking, you can read it, and you can probably use for the next project when you're detecting the windows. Like, no, sorry, not detecting. Let's say you have detected the window in the first frame, and you don't care about detecting it frame by frame. You can basically track it. Like, that's another option you can use it. So that's for this lecture today, and we'll see you next time.